So we'll look at one more quick example of using inheritance to implement yet another kind of counter. And then we'll move on to some new material. All right, so we got one counter that wraps around when it hits integer max value, goes back to 0. We've got a second counter that stops counting when it hits integer max value, and that's it. If you want to, you can implement a third kind of counter. This time it throws an exception when it hits integer max value. So you might want to do this in a case where you need a counter, you count up to some maximum value, and then trying to go past that value is an error. Right? So you might consider taking our existing counter class and extending it and having it throw an exception when it hits the largest possible value. Now it turns out this isn't the best idea, but we'll talk about this maybe towards the end of the lecture. Okay, so once again, to extend the counter class, right, you use the keyword extends. Right? So throwing counter is going to be the child class of the counter class. Again, notice that there's no fields here, right? So yes, we have a counter. We don't need to keep track of the value of the counter inside this class because the parent class or the superclass has the field called value that keeps track of the value. Right? So there's no need to declare any new fields here. Oop. Okay, we have some constructors, right? So a constructor that initializes the counter to 0. So one way to do this is to call the superclass constructor passing in 0. Right? We've got another constructor that sets the counter to a specified value. So again, we can call the superclass constructor to set its value. Right? Now remember, when you're implementing a constructor in a subclass, the first line of your constructor is always a call to another constructor. Right? So here I'm calling the superclass constructor in both cases. Right? In the previous lecture, I showed you how to use constructor chaining instead. At some point, though, you have to initialize the counterpart of the throwing counter. So you have to call the superclass constructor at some point. Right? Okay. The advanced method is straightforward. We want to throw an exception when the counter hits integer max value. Right? So we simply check, is the value not equal to integer max value? If that's true, add 1 to the value. Otherwise, throw an exception. Right? And that's it. You're done. You have access to this dot value, right? Even though it's not declared in this class, right? Because it belongs to the superclass, right? And we inherited that field. And the superclass, the access of the field in the superclass is protected, right? So this child classes have access to that field. All right, so you've now got 3 different counters, and you could cook up different ones if you wanted to. Right? Okay, so there are different ways to do this. So one of the problems with programming is that there's always more than one way to solve a problem. So there's another way to implement these counter classes. Right? So the only thing that differs in the counters is that something different happens when you hit the maximum value. Right? And so when we used inheritance, we just changed the way advanced behaves in those cases. Right? But it turns out there's another way to do this. So you can implement a single counter class, and then you can pass in an object that tells that counter what to do when it hits integer max value. Right? So your alternative here is to encapsulate the behavior of what happens when a counter is advanced past its maximum value in an object. Right? And then you can make that object a field. You can have a field of your counter class, right? That's an object that determines what happens when your counter hits the maximum value. Right? So I'm not going to actually do that example here. It's not hard to do. But there are lots of different ways to solve this problem other than just using inheritance. Okay, now what about this equals method? Right? So remember when we talked about equals, there were 2 different ways of implementing equals. There's getClass and there's instance of. Right? Instance of matters when you are trying to implement equals in an inheritance hierarchy. Right? So the question is, we now have a hierarchy of counters. Do you want to have different types of counters be equal to one another? Right? So you have a throwing counter and you've got a stopping counter. Right? Their values are both 5. Should they be equal? Right? So the answer is it depends. Right? So if you want that to be true, then you have to use instance of in equals. right? So what happens if you use getClass in equals? Right? So remember what getClass does. GetClass returns an object that corresponds to the class of an object. Right? When you use getClass in equals, what you're saying is two things are equal if and only if they have the exact same class. Right? So here's equals for our counter. This is for the superclass, right? So the counter class. If you implement equals using getClass, it's pretty easy to do. Well, it should be easy to do at this point in the course. Right? So we're going to use getClass to check, right? Is the class of this counter, which is just big C counter, right? Is it exactly the same as the class of that object there? Right? If they're different, then this method always returns false. Right? So if you try to compare a counter to a stopping counter, right? The type of OBJ is stopping counter. Right? So counter is not equal to stopping counter, so this always returns false. Right? So in this example here, right, we've got just a plain old counter and a plain old counter. Their values are both 0. Right? So if you try C1 equals C2, you get true. Right? Here we've got a stopping counter and a second stopping counter. Right? C3 equals C4 is also true because their values are both 0. Right? But as soon as you try to do a mixed comparison, right? So here we've got a counter and a stopping counter, right? C1 equals C2 is false because the class of counter is not the same as the class of stopping counter. Right? So here you've got two counters with the same value, but they're not equal according to our implementation of equals. Right? Similarly here, you've got a stopping counter and a throwing counter. Right? Is C3 equal to C4? The answer is no, because the class of stopping counter is not the same as the class of throwing counter. Right? So that's what happens when you use getClass. So in this particular example, where you're comparing counters, it kind of makes sense that you want to compare different kinds of counters for equality, right? Because all they have is just a value. So two counters with the same value, maybe they should be equal, even if they have different types, right? So this is where instance of comes in handy. Right? So if you change if you change equals in the class counter, right, you end up with the following implementation of equals. Right? So here we check if is this thing OBJ, is that an instance of counter? Right? Now remember what instance of does. Right? Instance of tests, is that a counter or any subclass of counter? Right? So if OBJ is a stopping counter, then instance of returns true. Right? If OBJ is a throwing counter, instance of also returns true. Right? And so this lets us get past this if statement in order to compare two counters by their value. Right? So even though OBJ is a, say, for example, a stopping counter, I can still cast OBJ to a plain old counter. Right? And the reason I can do this is because subclasses are substitutable for their parent classes. Right? So if OBJ is a subclass of counter, then I can substitute OBJ for any counter object. Right? Which means I can cast OBJ to a counter as well. And now I can compare their two values that way. Right? So now counters of the same type are still equal. Right? So two counters with the same value are equal. Two stopping counters with the same value are equal. Right? But now two counters of different types, as long as they have the same value, they're also equal. Right? So a counter and a stopping counter whose values are both 0, that now prints true. Right? Stopping counter and a throwing counter whose values are both 0, that also prints true. Right? And so you have to use instance of if you want to do comparisons of different classes in an inheritance hierarchy for equality. Right, any questions about that? Right, so that's the explanation of why you needed that second version of equals. Right? If you're not in an inheritance hierarchy, just use getClass. If you are in an inheritance hierarchy, you have to consider using instance of. Right? Otherwise, mixed type comparisons don't work, or are always false. All right. This leads us to the next part of inheritance, right? And that has to do with how many types an object actually has. Right? So if you're a big O object, if you have a big O object, that only has one type. Everything else in Java has more than one type. Okay? So an object's types include its own class type, right? So when you say public class blah, right, the blah is one of its types. Right? But the type of that object includes all of its ancestor classes as well. And so that means every object in Java, one of its types is big O object. Right? So one of the types of string is also big O object. Right? All of the interfaces that your class implements, those are also part of its type. Right? So do I have an example here? Yeah, so here's an example. Right? So here's our class point2. Right? Now we know point2 extends object because everything extends object in Java. And point2 implements comparable point2. Right? So the point2 class actually has three types. Right? It has the type point2, it has the type object, and it has the type comparable point2. Stopping counter extends counter, implements comparable counter. So it actually has four types. Right? So it has its own type, so it's a stopping counter. Right? It has the type of its superclass, so it's also a counter. Right? It has the type of all of its ancestor classes, so it's also an object. Right? And it has the type of all of its interfaces, so it's also a comparable counter. And finally, one more. Right? So string turns out to implement a whole bunch of interfaces. Right? It implements 1, 2, 3 interfaces. So it has all of those types. Right? It has its own type string, and it has the type of its superclass, big O object. Right? So string actually has 5 different types. And so this is related to the concept called polymorphism, which is another term you'll see if you ever read any of the object-oriented literature. Right? So the dictionary definition of polymorphism is the condition of occurring in several different forms. Right? So you can see in Java, right, one type, right, one class string actually has 5 different types. Right? So Java has what's called subtype polymorphism. Subtypes are substitutable for their ancestor types. Right? And that's made possible because the type of an object includes the types of all of its ancestor classes. Right? So string, right? A string object is always substitutable for a big O object. Right? Similarly, a string object is always substitutable for a serializable object. It's always substitutable for a comparable string object, and it's always substitutable for a car sequence object. Yeah. Right. Okay. So when you declare a variable in Java, like this, right, counter C, right, what you're saying is that the type of C, right, its declared type is counter. Right. So counter C declares a variable C whose declared type is counter. Right. So what does that mean? Right. So that means I can use C to do different things, right? So I can store the value null in C, right? Because null means no object, so any reference can store the value null, right? I can store a reference to a counter object in C, right? And I can store a reference to an object having a type that is a descendant of counter, right? So in other words, I can store an object of any subtype of counter, right? So I can store a throwing counter or a stopping counter or a wrapping counter. Wait, we don't have a wrapping counter. I can store a stopping counter or a throwing counter in a reference, in a counter reference. Right? So the declared type of a variable or field or parameter determines what operations you can perform. Right? So here we go. Right? So here I have obj. Right? Its declared type is object. Right? So the compiler is going to check, right, when I use the name obj, right, am I using the methods that belong in that are defined in big O object? Right. So here I have here I store an array list in obj, right, and then here I call toString using obj, right. That's fine because the method toString is defined in the class big O object. Right. Now, obj is actually an array list. or refers to an array list, right? So you might think, well, I can just add something to obj, right? So you might think that I can add the string hello to obj, right? But the compiler doesn't let that happen. Right? So if you try to type that into Eclipse, the compiler will immediately flag that as an error, right? And it'll say that obj is a big O object, right? And big O object doesn't have an add method in it, right? So the declared type determines what can you use that name for, right? If I declare obj to be a big O object, I can only use obj as though it were a big O object, right? I can't use it as an array list, right? Even though it really does refer to an array list. Right? So here I've got T, right? And I've declared T to be a set. Right? Now, set's an interface, so I have to pick a class that implements the interface if I want an object. Right? So I'm going to pick a tree set and store a reference to that in T. Right? That's fine. Right? Tree set implements the set interface. So a tree set object is substitutable for a set object. Right? So I can store that in a set variable. Right? I can call add using T. Right? Because T is a set, and set has the add method. Right? What I can't do is I can't call the method first. Right? First is a method that belongs to tree set. It returns the first object in the set, right? Because tree sets are sorted, right? But I can't use first because I said that T was just a regular old set. Right? So that doesn't compile because T was declared to be a set and not a tree set. Okay, if you change the declared type, so if I say that T is actually a sorted set, right, then calling first is no problem, right? So sorted set is another interface, right? It's the interface that tree set implements in addition to the set interface, right? So sorted sets are just sets that are sorted, right? And the sorted set interface declares the first method, right? So here you can use first now. Oops, sorry. Okay, anybody have any questions about declared types? Right? All right. So there's a second type now that's important in Java. Right? There's something called the runtime type. Right? So when you assign or initialize a variable, right? So you write something equals something, right? The thing on the right-hand side, that determines the runtime type of the object. Right? So when I say C equals new stopping counter, right? The declared type of C is counter, but its runtime type or its actual type is stopping counter. Right? So the declared type is on the left, runtime type is on the right. Right? So declared type is counter, runtime type is stopping counter. The runtime type determines which version of the method you get when you call a method using that object. Right? So for example, right, declared type, big O object. Right? Runtime type is counter. Right? If I use obj to call a non-static method like toString, right, which version of toString do I get? Right? Well, I don't get the big O object version of toString. I get the counter version of toString. Right? So the declared type determines which methods you can call. Right? So the object, I can call methods belonging to object. Right? The runtime type determines which version of the method actually runs when you call the method. Right? So obj toString ends up calling the counter version of toString, right? And not the object version of toString. Right? So if you consider the following method here, right? So it has a parameter of type big O object, right? And it calls, it calls toString using obj, right? Then it doesn't matter what object you pass to this method. Right? It's the runtime type of obj that determines which version of toString you get. Right? So for example, right, I have a string s, and I pass s to the print method. Right? Which version of toString do we get? Well, we get the string version of toString. Right? If I make an array list T, and I pass that to the print method, right? So print As far as print's concerned, obj is just a big O, is a big O object, right? But the version of toString that you get is the array list version, right? And finally, if I take date, right, a date object, and store that in an object reference, big O object reference, right, and I pass O to the method, right, even though that's declared to be big O object, right, when this method runs, right, it's the runtime type of O that determines which version of toString I get, right? So the runtime type is date. So we get the date version of toString in this example. Right? So declared type, which methods can you call? Right? Runtime type, which version of the method gets called? Right? Okay, now look in this toString. So here, right? If I take that printer class and compile it, it compiles just fine. Right? So the compiler is perfectly happy with this code. Right? You can then write some program that uses your printer class and calls print. Right? And then that object that you pass in, it gets printed using by calling the toString method. Right? But the compiler can't determine which version of toString gets called in the print method. Right? It still manages to compile the printer class without any issues. Right? So the actual version of toString that is called, you can't actually determine that until runtime. Right? So using the runtime type to determine which version of a method is called dynamic dispatch or late binding. Right? It's called dynamic dispatch, right, because the compiler doesn't know which version of toString to call. Right? The Java virtual machine is responsible for figuring out which version of the method to call, and that happens when you run the program. Right? So that's why it's dynamic. Right? It doesn't happen until you run it. Right? Dispatch is a fancy term for saying which version of the method do I call. Right? Late binding means the same thing. Right? Binding is which version of the method do I call? Right? Late simply means it happens at runtime rather than compile time. Right? So that print example there, that's an example of the power of polymorphism. Right? So remember, objects have more than one type in Java. Right? So this print method relies on that fact. Right? I can call this method with any object, right? Not just big O objects, any object, and it works. Right? Why does it work? Because all objects in Java have the type big O object. Right? So as a programmer, you can write a method, right, using the contracts or the interface, whatever you want to call it, right, using the interface of any ancestor type, right, and the method should work for objects of any descendant type. Right? So in other words, I can write this print method using just the documentation for the object class. Right? The object class says it has a toString method in it, so I can write that. Right? This method is guaranteed to work, right, and do exactly what the object version of toString says it does, right, regardless of which object I pass into the method. And so there's tons of examples of this if you look at the classes in the Java standard library. Right, so there's this class called collections that operates on lists and sets. Oh, sorry. Do I have a link here? Oh, I do have a link here. Okay, so let's see if it's going to open. Okay, so here's the collections class. Collection, wrong link. Sorry. There we go. Collections. Oop. Okay. Let's see. I guess add all works. So you've got this method called add all, right? This funny notation here, t ... elements. Right? This just means you can pass in one or more elements to add to a collection. Right? What does the method do? It takes all of those elements and adds it to the collection C. Right? What type of collection does it add it to? Well, it looks like it's just this thing called collection. Right? And if you look at the documentation for collection, right, it says it's the root interface in the collection hierarchy. A collection represents a group of objects known as its elements. That sounds familiar. If you actually dig a little bit deeper, you'll realize that a collection, right, sets and lists are collections. So you can pass any set or list in for C, right? And this method will add all of these elements to your set or list C. Right? And there's a bunch of other methods here as well, right? So here's binary search, right? Binary search will search any list as long as the element type implements comparable, right? So you can pass it in a linked list, you can pass it in an array list, you can pass it in any type of list, and it works, right? Why does it work? Because of polymorphism. Oh, I guess there's one more thing to say. So how does so inside binary search, what is it actually going to do? Right? So if you remember binary search from CISC124, you know that you have to compare elements in the list. Right? So how do you get elements from a list? You use the get method. Right? So if you go and look at the source code for binary search, inside you're just going to see a bunch of calls to list.get. Right? And then when it's going to get an element. And then it's going to compare them using compare to. Right? How does the method know that it can do this? Right? Because it says it takes in a list, right? And we know what methods lists have, right? How does it compare the elements? Well, we know that there's a compare to method for the elements. Oh, sorry. All right. Any questions so far? Okay. Oh, sorry. Where is it? All right, so this whole notion of a child class being substitutable for one of its ancestor classes is related to this principle called Liskov substitutability. Right? So Liskov substitutability was defined by Dr. Barbara Liskov and one of her students. Is that true, or is it her and one? I don't remember. It was either her and her student, or her and her supervisor. I don't remember anymore. So there is a formal mathematical definition for this. I don't care about the formal mathematical definition. Right? Basically, without being too specific, right? What this principle says is that if you have a subclass object, right, it must behave the same as objects of its supertypes. Right? So in other words, whatever methods a subclass object has, right, they have to work in the same way that the superclass version of the method works. Right? Now, the problem with this is that in Java, there's no way to guarantee, or there's no way for the language to enforce that this happens. Right? In other words, it's the responsibility of the programmer to ensure that this happens. Right? If you ensure that this happens in one of your inheritance hierarchies, then what that lets other programmers do is allows you to write code according to the contracts of the ancestor classes, right? And that code will always work and be correct if you pass in a subclass object, right? And that's actually really powerful if you think about it, right? So I can write some method, I can test it, right, according to its contract, right? And then that method is supposed to work properly regardless of which object I pass into it. Right? As long as the object that you pass in is actually a child class. Whoa, sorry. Okay, so how do you ensure that your child class is substitutable for its parent class? Right? Well, one of the things you have to look out for are any class invariants. Right? So remember what a class invariant is. Right? An invariant is a property that's always true. Right? A class invariant is a property of a class that's always true. Right? So for the counter class, right, its invariant is that the value of the counter is always non-negative. Right? If a superclass has an invariant, then the invariants of the superclass apply to all of the descendant classes. Right? So the invariant is a public feature of a class, so it gets inherited. Right? A subclass that fails to support the invariance of the ancestor class can cause correctly written code to break. Right? So that's the part that should bother you. Right? Causes correctly written code to break. Right? Okay, so counter says, right? The counter class says that its value is never negative. Right? So someone can come along and write this method called isOdd, right? And it takes in a counter C, right? Not just a counter C, it takes in any counter C, right? So it'll take in a stopping counter, it'll take in a whatever, a throwing counter, how do they implement this, right? So they took the value of C, right, divided it by 2 and looked at the remainder, right? If the remainder is 1, then it returns true, right? If the remainder is not 1, it returns false, right? If you look at the contract for counter, right, which says that the value of the counter is always non-negative, then you can pass in any counter object to this method, and it will always return the correct value, right? So you can test this value with every possible counter, and it will always return the correct value. Right? So in other words, this method is correct according to the contracts of the counter class. Okay, now, suppose that someone comes along and makes this thing called a descending counter. Right? Now, a descending counter counts down from 0 to integer min value and then wraps around back to integer max value. Right? So in other words, it's the opposite of our regular counter. Right? It counts down. And its value can become negative. Right? It's easy to implement. Right? You just extend counter. Right? Again, there's no field here, right? Because the value of the counter belongs to the superclass. Right? You can easily implement the constructors. You can easily implement advance or override advance. Right? You just decrease the value by 1 every time. Right? When it hits integer min value, it wraps around to integer max value. Right? And you're done. Easy peasy, right? The compiler looks at this, it doesn't care. Right? Because the compiler doesn't know anything about contracts for methods. Right? All it cares about is Java. Right? But what went wrong? Well, what happens now? So if I take this counter, right, if I take one of these descending counters and pass it to this method, right, if the value of the descending counter is negative, this is incorrect. Right? So negative 1 divided by 2, take the remainder, is negative 1. Right? And that's not equal to 1. So this method thinks that that counter is not odd. It thinks it's even, right? Even though negative 1 is odd. Right? So suddenly this method breaks. Right? So isOdd now fails when you give it a descending counter whose value is negative. Right? And that should bother you, right? Because this method broke, right? Just because someone went and made another class, right? They just made they subclass counter and made their own class, right? And now this method, which you can't possibly know about every subclass that a counter can have, right? Suddenly this breaks, right? Strictly speaking, this programmer is correct. This programmer is incorrect. Right? The creator of the descending counter class did not ensure that the invariant of counter was preserved. Right? You now have a counter whose value can be negative. Right? And this person here, right, wrote that method correctly assuming, that the value of the counter will never be negative. Right? Okay, does anybody want to criticize this programmer here? You should all have your hands up. Because there is a way to fix this method so that it works with a negative value too. Right? So if you're going to check for an odd value, don't do it this way. Right? If you want to check if it's odd, right, don't check that the remainder is 1. Right? Check that the remainder is not 0. Right? Because now it can be negative 1 or 1. And now this works. Right? So you can argue that maybe this person shouldn't have written isOdd the way they did. Right? But even though they did write it the way they did, they're still correct. Right? So even though they wrote it this way, which you really shouldn't, but anyway. Right? This is technically correct given the contracts for the counter class. Right? Notice that the compiler can't help you in this case. Right? There's no way for the counter to read the documentation for the counter class and realize that there's an invariant. Right? So there's no way for Java to help, the Java language to help you here. This is a programmer responsibility. Okay, so if the subclass has to respect the parent class's invariants, does that mean that the parent class's invariants can't be changed? Right? The answer is no. Right? So you are allowed to modify the invariants that you inherit, right? As long as the modified invariants satisfy the inherited ones. So the invariant for counter class simply says that the value of the counter is never negative, right? So that means you can go ahead and implement this thing called a range counter, right? So a range counter counts between two different positive values, or two different non-negative values, right? So you can have a counter that counts from 5 to 10, for example, right? It's easy to implement, right? So you just extend counter, right? You now store the minimum and maximum value that you want to count between, right? And then in advance, you just make sure that the count never goes outside min and max, right? It's dead easy to implement, right? Slightly interesting because now you have to add extra fields to the class, right? But otherwise, it's straightforward, right? So here, the range counter now says it has an invariant, right? Where the value of the counter is always between min and max, where min and max are both not negative values, right? That's fine, right? If you pass a range counter to our previous isOdd method, right, it works fine, right? Because its value is always non-negative, right? It's just that its value is between a more restricted set of values than a regular counter, right? But that is acceptable, right? So it is possible to change the invariants. You just have to make sure that the parent invariants are still respected. Right? All right, so there's we now need to look at methods. So there's if you haven't, there is a notebook called Substitutability that contains all of the classes and discussion for this lecture. So there's something called the shape class, but I'm going to describe it in the lecture slides as well. Okay, so the shape class is something called an abstract class, which we haven't seen yet. Right? So an abstract class is a class that you can't use to make objects directly. Right? So I'm going to have a class called shape, but I can't make shape sorry. I'm going to have a class called shape, but other programmers cannot make shape objects by writing new shape. Right? You might think, well, that's weird. Right? Why am I making a class where I can't make objects? Right? So the purpose of an abstract class is to serve as a common superclass in an inheritance hierarchy. Right? So in other words, I want all of my subclasses to be shapes, big S shapes. Right? So what are you going to put in this abstract class? You're going to put all the methods that are common to all shapes. Right? And you're going to put in all the fields that are common to all shapes. Right? And I'm going to stick them in this shape class. Right? And so it's an abstract class, meaning I can't make shape objects directly, right? But it defines all the stuff that's common to all shapes, right? If you were to draw the UML class diagram for this class, you would write the name in italics, right? Otherwise, it looks like a regular class. Okay, so when you make an abstract class, you just declare it to be abstract, and that's it, right? So I have a class called shape. It's got some fields, some constants, and it's got a little description here. Right? So my abstract shape class is the superclass for 2D shapes that have independent width and height. Right? So in other words, you can change the width and height of a shape independently. Furthermore, the width and height have a minimum value of 1 and a maximum value of 100. Right? So the size of a shape is always between 1 and 100. Sorry, the width and height of a shape is always between 1 and 100. Now this is the superclass, right, for all shapes. So its fields, width and height, right, these are the fields that all shapes will have, right? The subclasses probably want access to them, so we're going to mark them protected. Right? Marking them protected lets the subclasses access width and height by name. Right? And then there's some constructors and some methods. Right? Namely, there's width, which returns the width of the shape. Right? There's height, which returns the height of the shape. And then there's this method called area upper bound. Okay, so if you've got a shape that's got a width and a height, right, so that's its width, and that's its height. Right. And then you have some shape, the actual shape, let's say it's a triangle. Looks like that. Right. So the actual area of the triangle is smaller than the area of the rectangle that encloses it. Right. Area upper bound, right, is a method that returns an upper bound on the area of the shape. Right. So all it does is return this width times this height, right? It just returns the area of the rectangle that encloses the shape, right? Notice the documentation goes on. It says some shapes have a complicated geometry, right? And computing the exact area of the shape is difficult. So if you had some squiggly shape, right, some blob, amorphous blob, right, it's actually very hard to compute the area of that thing, right? So instead, you might call this area upper bound method and get a value for the area that's at least equal to the area of the shape. It can be bigger. Right? Subclasses should override this method if they can provide a tighter upper bound. Right? So if you implement a triangle, you should actually return the area of the triangle because you can easily calculate the area of a triangle. All right, so you have a public method inside the abstract class. And finally, we've got set dimensions, which changes the width and the height of the shape. Right? So it takes in the width, it takes in the height. It makes sure that the width is between min value, make sure that the width, it tests if the width is less than min value or if the height is less than min value, and throws an exception if it is. Right? It tests if the width is greater than max value or if the height is greater than max value and throws an exception if it is. Right? Otherwise, it just sets width and height to the desired width and height. Okay, so now using the shape class, you can go ahead and start to write a bunch of methods that do something with shapes. Right? When you write your methods, you're going to use the contracts that are here. Right? So you're going to use that contract here, you're going to use that contract there, right? That contract there, and so on and so on and so forth. Right? So in other words, you're just going to look at the shape class and write some methods that manipulate shapes. Right? You're not going to look at the documentation for the child classes because at this point we don't even know what the child classes are. Right? So I can write a method that randomly changes the size of a shape. Right? This method passes every possible unit test that you can write by looking at the shape class contracts. Right? So here we got random scale. Right? Takes in a shape object. Right? Computes a new width and height. Now, don't worry about the details. Right? All this does is it changes the width and height by a small amount. Right? Something like plus or minus 1/2 of, between plus or minus 1/2%. Right? That's all it does. Right? It tests, right? So it computes a new width. It computes a new height using the current width and the current height. Right? It tests is the new width greater than or equal to 1. And so it tests if the new width and the new height are valid. If they're valid, it changes the dimensions of the shape. Right? If it's not, it leaves the shape unchanged. Right? That method there is perfectly fine the way it's written. Right? In other words, if I call set dimensions, right, it changes the, it doesn't matter what shape I pass in. The size of the shape will change to some random width and height, right? And no exception will be thrown, right? So as far as we're concerned, this method is correct. Right? Okay, so we have the shape class now. Now the problem is someone comes along and starts implementing some child classes. Right? So we have a child class called rectangle, right, that inherits from shape. Right? And then we decide that we also want this shape called square. Right? And we're going to try to inherit from rectangle. Right? Okay, so many methods place restrictions on their parameter values. Right? So for example, set dimensions requires the width and height to be between 1 and 100. Right? If a subclass overrides a method, right? So a subclass decides to override the way a method behaves, then it must accept all of the parameter values that are accepted by its ancestor classes. Right? So in other words, any subclass of shape has to accept a width that's between 1 and 100, and it has to accept an independent height that's between 1 and 100. Right? So the problem with square is that squares don't have independent widths and heights. Right? So as the implementer of square, right, you might decide to change set dimensions so that it throws an exception if the width and height are not equal. Right? So it's easy to subclass rectangle to get square. right? You just extend rectangle, throw in a constructor, and then override set dimensions. Right, here we're going to test, is the width and height, are they different? And if they are, we're going to throw an exception. Right? If they're the same, we're going to go ahead and call set dimensions. Right? Notice the use of the keyword super here, which I'll explain on the next slide. Okay, when you override a method, right, it's often convenient to call the superclass version of the method. Right? So for set dimensions in square, it's convenient to call the set dimensions method that we inherited from rectangle in this case, right? And let the inherited version of the method do the work that it needs to do. Right? So instead of setting the width and height myself, I'm just going to call the superclass version of the method to do it for me. Right? So the square version of set dimensions calls the rectangle version of set dimensions. Right? That version of the method tests if the width and height are between 1 and 100. Right, and then sets the width and height appropriately. Right? If you find that you want to do this sort of thing, right, then the way to call the superclass version of the method is to write super dot in front of it. Right? Don't write this dot. Right? If you write this dot here, you end up calling this version of set dimensions, right, and it becomes recursive. In this case, it becomes infinitely recursive. So whatever you do, don't write this dot set dimensions here. Right? To call the parent version, use the keyword super. Now, what's the problem here? The problem is that, right? That condition that we just added here, right? If the width and height are different, that's an error, right? So the problem is, when you go back to this method here, which we are pretty sure is correct, right? This method here computes a random width and a random height, right? Because they're random, they're almost certainly not equal. Right? So when you call set dimensions with a square, right? This now, whoa, right? This now, what's going on? This now throws an exception, right? Because the version of set dimensions that gets called is the square version of set dimensions, right? So this now throws an exception, right? Or an exception is now thrown in a method that we previously thought was correct. Right? Which is something you don't want to do, right? Okay, so in this example here, right, we've got a subclass that adds an extra restriction, right, on the values that are passed into the method that the parent class did not have. Right? So what that means is any code that's written with the parent class contracts now potentially fails when passed in a square object. Right? And that's what's not supposed to happen. Right? So whoever implemented the square class did this incorrectly. Right? You are not allowed to add that constraint. Right? And now you might ask, well, how do I implement square if I don't have that constraint? And the answer is you can't implement square in this inheritance hierarchy. Right? But the shape class told you that to begin with. It said this is a hierarchy for classes that have independent widths and heights, right? And circles and squares don't have that. So there's no way to sensibly do this, unfortunately. Right. Okay, I guess that's a good place to stop, and we'll pick this up in the next lecture.